name is Ilias Syrigos. I'm a senior research engineer in the University of Thessaly, located in Volos, in Greece. And in this slot, I will present you a brief overview of the TANGO reference architecture. So here's the outline of my presentation, in which I will provide an overview of the architecture, some considerations regarding the data space connector we are using, and finally an instantiation of the architecture in a relevant use case from a pilot in the project. So I will now begin with the overview of the architecture that we have been very carefully designing, considering several key factors. First, of course, were the project's technical objectives for delivering a decentralized, trustworthy, and secure data sharing framework. Second, it was the need for integration of the various technological offerings and components we are delivering in the project, considering their interfaces, their interdependencies, and of course their deployment requirements. We also need to consider the requirements from the use cases and the pilots that evaluate our delivered solutions. And finally, we need to align with widely adopted partners. So this is a three-layered architecture that incorporates trust, management, and user layers in order to ensure a secure and seamless data exchange within the whole TANGO ecosystem. So in the trust layer, we support functionalities that are related to authentication, to authorization, and encryption. While in the management layer, we support the fine-grained orchestration and configuration of both platforms and individual components. Finally, in the user layer, we offer several AI and analytics tools for which the users, the data consumers, are able to leverage. So the whole architecture follows a microservices approach, with every module that is developed being containerized, and it also supports the distributed deployment of these containerized microservices across multiple environments and different physical locations. Furthermore, it aligns with both Gaia-X and IDSA principles in order to ensure the secure and sovereign data exchanges, but also for interoperability with potentially other ecosystems or other data spaces. So, in overall, we of course build on the principle of data space initiatives, but we are not in fact actually focused on building a complete data space. And we rather adopt the concept of the connector, and this is what we extend by providing extra privacy, security, and also all the AI tools and data analytics that are offered to data consumers. So the architecture is modular, meaning that it enables a detailed configuration of components and also on-demand activation of these components using cloud-native approaches based on Kubernetes, and also configuration using Blueprint YAML files. All this in order to support both the use case pilots of the project, but also any other future potential use case. We also incorporate front-end applications and user interfaces in order to provide the users with a transparent way of interacting with the whole platform, and everything remain hidden from their eyes, whatever it is going through under the hood. So the technical components of TANGO are distributed across 3 different locations. First, we have components deployed in an organization's infrastructure, which organization plays the role of the data or data service provider, and where we deploy a TANGO connector. From there, whenever data access needs requires authentication, authorization, usage, or access control, is accessed through this TANGO connector. Secondly, we have components that are deployed on an end user's device, which could be a smartphone or perhaps a personal workstation that supports containerized deployment, in order to provide onboarding applications, authentication, and encryption applications. Moreover, we also have in the end users machines various front ends of the user interfaces, and also some mobile applications we develop in the project. And last, components are deployed on a centralized infrastructure on the trust anchor of this ecosystem, where we have the so-called management connector, where mainly management services reside, such as the deployment orchestration that handles deployment of connectors and modules on the premises of the different organizations, the App Store that stores the containerized images of the modules we are developing, and the blueprint repository that stores the configurations files for each of the use cases. Now, central to this architecture is the data space connector, which we have decided to use an existing open source implementation rather than building one from scratch, so as we are able to leverage the already developed and already tested components, ensure compliance with the existing approaches of IDSA and Gaia-X, and mainly focus our efforts on developing our own solutions that are that has been then integrated with the connector. So we have explored several open source implementations of connectors, such as the data space connector, which was originally developed by Fraunhofer, the Eclipse data space components, and the FIWARE data space connector. So in order to select one of them, we consider the following criteria, which were the alignment with the architecture that we have designed, the support for decentralized identities and SSI in general, to have a very large and very active community, and also we consider the level of complexity for both configuring and deploying this connector. So based on all these criteria, we opted to go with the FIWARE data space connector. This connector implements the DSBA technical convergence recommendations that aim to converge IDSA, Gaia-X, BDVA, and FIWARE into a common technical approach regarding data space. This connector is built upon authentication that is based on distributed identities and OpenID Connect protocols, and also on authorization that is based on attribute-based access control following the architecture of PDP. So we have adopted this FIWARE data space connector, but we have implemented our own solution for both SSI and PDP authorization, as well as we have integrated all the other technology offerings and technology solutions we developed in TANGO with this connector. So the connector involves consists of several individual components, such as, for example, the portal, that is the interface for the user to interact, the verifier that provides authentication capabilities, and several other modules that are related to SSI. A gateway API that acts as the policy execution point, a policy decision point, an authorization registry that stores the data providers' usage policies for the data, and finally, a linked data backend that stores the actual data that is being offered by the provider. So next, I will provide an example use case from a project's pilot in order to showcase how this architecture works. So this pilot is the smart manufacturing pilot of Flanders Makes that is focused on the digital twin for quality assurance in 3D printing operations. So it involves different stakeholders that are both internal to the organization, such as its own employees, as well as stakeholders that are external, which are the customers of Flanders Makes. There are several aspects here that are being involved, such as data sharing of proprietary data files, which are the design files of the objects that are that need to be printed. AI model training using large data quantities and also proprietary data, and data analysis of the printing result and the measurements that are being generated during printing for the technical experts of the company and also for the customers. So below is a diagram that shows a typical flow from the left to the right, where we have every customer of Flanders Make providing a proprietary CAD design file of its own object and uploads them in a shared repository with this design being encrypted. Then the technical expert downloads the encrypted designs and combines them into a single job file, which uploads to the printer to start the printing process. So during printing, there are a lot of measurements that are being generated, and these measurements are used for both AI training and data analysis for the customers and the technical experts. So during this flow, there are many interactions with the TANGO components that are required. As there is a lot of data access, this means that there is a need for onboarding, for authentication, authorization, and encryption, but it's also a requirement for efficient data analysis and also AI training. So in order to instantiate the architecture for this specific pilot, we need to deploy a specific setup where we deploy a connector at the organization's premises at Flanders Make, which is responsible for issuing verifiable credentials for its own employees, onboarding the employees, authenticating both employees and customers, authorizing through PEP and PDP data access, encrypting and decrypting data, and also providing the data analytics and AI tools. We also deploy a connector at the customer's organizations for issuing verifiable credential for its own employees, which are, of course, customers related to Flanders Make, and also onboarding them in the ecosystem. And then we have several modules that are deployed on the user's device for onboarding, the SSI wallet for used in the authentication process, and also encryption and decryption modules. And here we have a graphical demonstration of the workflow where the technical expert downloads the encrypted designs that have been uploaded to the shared database repository of Flanders Mail. So the flow is that the expert first logins at the portal, and then using his SSI wallet, he exchanges verifiable credentials with the verifier and performs the whole SSI process. So on a successful completion of this process, he receives an access token, a JWT access token that corresponds to his, let's say, identity. He then requests the desired data, the encrypted design, by attaching the access token in his request. Then this request is being authorized by PEP and PDP, which decode his access token and map his role, if he is a customer or if he is an employee, with the pre-configured access policies of the data provider of Flanders Mail. So when this is successful, the data is then downloaded locally to the machine of the technical expert and can then be decrypted by the decryptor module. So the whole decryption process that I do not delve into many details here is performed in a distributed fashion and involves the providers, the consumers, and also the management connect. So this concludes my presentation. Thank you for your attention.